So I'll tell you about a lot of things. If you want to know way more details, please let me know, since it's really kind of an overview presentation. So I'm going to talk about, well, how robots can learn new skills. And let me, as I did my PhD about 8 kilometers away from Hollywood, allow me to start it with a movie. What you see here is actually the first robot commercial ever. This is from 1969, and the company Unimate just had presented this robot, and they were so cocky about it that they directly aired it as a commercial that at some point in the foreseeable future you will have its successor in your home. Now, this monster you won't have there. You will see it in a second why. That is quite clearly not the robot you would have in there. But the surprising thing is, this robot actually had all the features of modern robots. It was already, it was electric, it was computer controlled, it followed a desired trajectory, it had a relatively high speed controller. Basically every other industrial robot works exactly this way, but the scenario is still futuristic, right? Despite that these anachronistic 1970s, late 1960s family, which totally doesn't fit our futuristic feeling about that robot system. Now, the sad part is that despite all the advances, right? Our computers have become faster, have been smaller, cheaper, our actuators have become better, our robots have become smaller. We are nowhere close to actually making this the standard at home. In fact, if you wanted to do it today, you would maybe be a bit better than back then. So back then you wouldn't have needed 5 good engineers who would actually do all the programming, since they did it for the very first time, and so on. But today we would still have to hack up this complete task pretty much in the same way as they did, just with a nicer programming language, a little bit better, much better interfaces, so no Lochkarten, I don't even punch cards as they used back then for the computers. But so our complete successes in computer science have not translated into robotics. And in the end, it would, in terms of all the technical work, which is not the computing work, this task would be as difficult to program today as it was difficult to program back then. So, why is this? Why don't we have such robots today in our environment? And well, when you look more, yes.
Back then, was this real, or was this Hollywood fake?
No, so some parts were Hollywood. One part was Hollywood fake, very clearly. The part where they opened the bottle, that was completely faked. Everything else was actually programmed. And
it's not shortcut somehow.
Well, the thing is, there is a very quick shortcut. They basically made it follow one particular trajectory. If any of these objects had been at a different location, nothing would have worked, right? So everything was nicely pre-positioned at exactly the locations where you need it, such that it would work out precisely in the way it did in the video. But except for the opening of the bottle, I don't think anything was faked in here. Yeah. The problem is just this. If you would do it today, the biggest difference would be we don't no longer use punch cards. We actually write the code on nice computers. But back then you would have used some sophisticated engineers. Maybe today you could use bachelor students for it. But the difference is minimal in terms of what really would make out the difficulty of the task. In fact, when you look at this here, this is one of the hundreds of car manufacturing factories. These work exactly according to the same principles as that robot from 1969. Not even the advances of robotics of the 1980s have fully translated into commercially available industrial robots. And what they do is really, they program the robot to follow a trajectory at the accuracy of about 150 micrometer. So 150 micrometer, Just take your favorite ruler and look at how big a millimeter is and divide it by 10. Then you get a feeling of how accurate that is. Basically a hair. And nothing would work in any of these factories if there is too high an uncertainty in there. These robots are in fact so dangerous that they're behind cages, and so that if you don't run into them when it's only happened twice. I think that people ran into them. One was at Volkswagen just 2 years ago, and one was in the 1970s when a drunken worker fell into a cage from the top. Both cases were kind of fatal. And the technique is exactly the same. But even when you look now at the more modern robots, like you see here a lawnmower, or you see here the Roomba, and a lawnmower usually follows just a wire in the ground and according to a pre-specified trajectory, at least 90% of the models. The other 10% of the models follow the exact same ideas of the Roomba, which, if any of you ever had one, I had one for a while, you basically start to arrange your furniture so that it doesn't get stuck. Because its only sensor is, does it bump against something, and then it turns by a random amount of degrees. So what went wrong? Well, the problem, of course, is classical roboticists are classical engineers. They don't even have a statistics education. And we really start to adapt the task to the robot and make it work precisely for that environment. And when you put it into it, it's actually really an educational problem, because we train engineers in exactly the feeling which Rutherford had about physics, that if you need statistics, you have a bad physics experiment. And in the same way, we think about robotics. If you need any form of probability, most classical roboticists will already say, oh, no, we haven't even studied that in our diploma engineering or master of engineering degree, since they simply, avoid it altogether. Now that is something which we in robot learning try to change. Now I want to take you into my journey and first give you a tiny bit of background with an introduction, then give you a feeling of the kind of learning problems which we usually have. This is going to be super superficial for the ones who do machine learning. I apologize to that half, but I'm pretty sure that half of you are probably not doing machine learning. So maybe that is suitable and useful. And then I'm going to address the question of how we can learn first elementary simple movements and compose more and more complex behavior and finally adapt this behavior to adapt to humans and learn interaction. And finally, I'm going to give you an outlook and a conclusion. So let's start with the only really adaptive robot we know. This here is a human being doing a task which I particularly liked. It has a paddle, and on the paddle it tries to bounce a ball. The ball has a string in there. Now this human robot has an internal state, a proprioceptive state, which is joint angles and joint velocities. And it has an external state, which is the ball position and the ball velocity. Everything all right?
I'm just wondering if you try to find an adapter so that because the picture is so bad, right, the quality.
Yeah, I really don't know. It's the VGA cable here, I think, which is the problem.
The HDMI input, it's always the problem with this projector.
Anybody has a USB-C adapter to Thunderbolt? I think this is Thunderbolt. I didn't take mine.
This is HDMI.
Is this HDMI?
Yes.
Okay. Ooh, beautiful. Let's give this a shot. Okay, now we get the spiral of death. And that works even more beautiful. Now this is interesting because it uses not on my screen here, it doesn't use the complete screen. Okay, now it does. All right, this looks much better. Okay, VGA, big problem, I see. So, yeah, I was just explaining state is ball position, ball velocity, and arm position, arm velocity. Actions for the human are, of course, muscle stiffnesses, which we send and muscle equilibrium points we send down to the muscles, which for the robot would actually be motor torques. We usually sum up all the states in a vector called x and the actions in a vector called u. And this gives us obviously, well, the two key parts of interest, since the state is something which we can sense and estimate, while the action is what we actually want to generate with the learning system. And well, autonomous learning robot system would usually be modeled by a policy which gives us actions in different states. And usually we're talking about a policy and not about a model. Because in a model we are trying to represent somehow reality, while with a policy you're actually trying to take out of the reality a part of it which you want to impress onto the system. So for that reason, well, we obviously need the teacher here, which tells us, well, which of these actions were good or bad in any form. And then, of course, well, whenever we do an action, our state changes, and we go from xt to xt plus 1. Now, a classical engineer would actually try to write down this particular as a function, would write down the mechanics, and try to get this as good as possible. While for us in robot learning, we nearly always try to directly model the system as a distribution, just already in order to facilitate learning, but also because it allows us to think about all the uncertainty in the world in a much better way. Now, next big question, of course, is how can we now model behavior? And in a way, in very classical AI, people tried for a very, very long time to do exactly that, right? They tried to come up with a very big set of rules, which tells us, well, how to do behavior. Well, they would do it with a search engine over many rules, and we all know they failed. So quite clearly, the counterpart in robotics of saying that you want to just have a function mapping you from state to action can actually also not really be enough. Instead, you really need stochasticity for exploration, since if you always try the same thing, well, there's obviously not going to be any learning. But more interestingly, it actually eases algorithm design. And by that, it eases it both in the terms of getting a simple algorithm, but also in terms of getting a simpler algorithm which is more efficient and much faster. And then finally, well, the optimal solution can actually be stochastic. This is something which really boggled my mind when I first realized it. But it can actually, you can very quickly construct control system or robot systems where a deterministic policy will always be suboptimal to a stochastic one. And so it's not actually, you need to have in this case some unobservable quantities in there, or partially observable quantities, but it's quite straightforward to show. And finally, when you're just trying to learn a solution from a teacher, reproduce a teacher, in this case you also want to model the variance of the teacher. So this brings us to the goal of learning stochastic policies, which are distributions over the actions, given the state, and some policy parameters which facilitate learning. Now we're interested, of course, not in just single state action pairs, but in whole trajectories of state, action, and so on. And using the assumptions from up to now, we can write down path distributions and, equally importantly, path rewards. So what would be learning from our perspective? Quite different from the way of how you would see it in a, well, how to put this, data-centric supervised machine learning lecture. For us, learning generically, well, has to deal with self-improvement. This here is an initial policy, and you directly see it fails. And subsequently, you see, well, different improved policies. After quite a lot of optimization on the different policies it has tried, you see actually a nice behavior. And in fact, this robot, it's about this high. It reaches a speed of 0.5 meters per second. and well, it doesn't fall over at all. It can go rounds and rounds and rounds for however long you want. So quite nice. So how do we do this? Well, what we really try to do is we try to maximize the scores of our teacher, the expected returns and from these scores, really along the complete trajectory. So with this, I hope I've put you into my shoes. And now I want to tell you about the two kind of learning problems we actually, how to put this, and need most frequently in order to obtain new policies. And the first of that is usually, not always, like if you were to today's master's thesis presentation of Simon, you have seen that you also can learn a lot from scratch. But in most cases, we humans, when we learn a skill, we don't start from scratch. Every one of us who has learned tennis knows it's the teacher takes you by the hand, shows you this is a forehand, this is a backhand. It's a totally awkward movement initially, and then it takes you 300 trials to get the first ball back over the net. But it gives you a good feel from what you can actually start at. And that's the domain of imitation learning. Given a path distribution, how can we actually produce the policy of it? And what we figured out is that what you basically need is a specific class of rewards, and one which really just measures the distance between the path distribution which you produce and the path distribution which you have observed. And distance, well, you could measure it with any kind of F measure, for example, the logarithm, in which case this would just become the KL divergence between these two distributions. In the simplest case, where you have to only allowed to do one action in your whole life, this would be just pairs of states and actions, these little asterisks, and you could try to reproduce simply this Gaussian. For path distribution, you would of course have to infer this policy, but it turns out that this is surprisingly easy, because the model appears here on both in the denominator and numerator, for example, by the logarithm, for the KL divergence, and cancels out so that you can do, if you have fully observed information, you can actually already do a hell of a lot directly based on samples. In fact, by just minimizing on samples the KL divergence, if you've observed everything about your state in action, you can do model-free one-shot learning and obtain a good imitation of your teacher. While if you have some unobserved information, you would need to do some iterations on this and use the model-based approach, which to fill it in an EM style. So that basically should persuade you it's relatively straightforward to derive the right kind of EM algorithms, or even one-shot regression-like algorithms to do imitation. It gets much harder in the moment when you're going away from this very specific reward of staying close to a trajectory distribution, and you want to go to, well, arbitrary rewards. And since in the arbitrary reward, oops, I don't know what's going wrong here. In the arbitrary reward scenario, you actually have here just a number, and here just a distribution. And you recognize directly this does not have any notion of data in the cost function we're optimizing. This is actually the core problem in all of reinforcement learning, that data gets into it somewhat artificial. In the value function methods, as Sutton and many others have been pushing them since the 1980s, is you basically take ideas from dynamic programming and optimal control, and you write them down in a form where they become some form of averaging. And by that, well, you can nevertheless treat your samples as if they came from the new policy with the new policy parameters theta, and by that do improvement. Similarly, you could of course do gradient descent, where you don't move sufficiently far away from your current policy, and therefore can also reuse your data. But both of these are relatively, how to put this, they're somewhat quite artificial solutions to it. And they also, well, the policy gradients really have the problem of small steps. while the greedy softmax value function methods usually have quite a big optimization bias and very fragile results. And what we then found, and this was for us quite impressive, that when people study how humans do both movement as well as in stochastic environments, and so when you add a lot of flow to it, or when you do kind of gambling problems, when there's a lot of stochasticity added to your own environment, just in very simple bandit scenarios, people do something very crazy. They don't jump to the best solutions they've seen, but they match distributions. They do some form of reward-weighted matching. So like in this quote up there, when learning from a set of their own trials in iterated decision problems, humans attempt to match not the best taken action, but the reward-weighted frequencies of their actions and outcomes. For us, this basically means, can we create better policies by matching the reward-weighted previous policy? Intuitively, if you again take this one action in your whole life scenario, and you would normally have started with this yellow distribution, yellow policy, where you would have now taken, well, actions which were bad, shown by this minus, and actions which were good, shown by this plus. Well, this would just mean try to grasp the pluses, except for the states where you have no good action, where you would rather stay close to the bad ones. And it turned out that you can understand a lot of the more esoteric reinforcement learning approaches, or which used to be esoteric, from exactly this matching kind of scenario. We actually found this directly useful from start, where we applied it for this little dog. In case you've seen Boston Dynamics' Big Dog, this used to be its little brother, and Boston Dynamics had distributed 6 of them. The bad part about it was that it has 3 degrees of freedom per leg, and if you were just going into one of these cracks, you would roll over and you would fall down to the side. So what we actually taught it here was to, well, get a negative reward, get a low reward when it slips in any form when it sets down the foot, and give it a high reward if the foothold is always stable, and would just learn a foothold policy. There, this made intuitively directly sense, this reward-weighted matching, but it turned out that it even was just a special case of just slight variation of the classical optimal control problem. If you would write down the optimal control, the reinforcement learning problem as an optimal control problem, where you know everything, you would end up with maximizing the expected return, subject to, the path distribution being a path distribution. If you add one single constraint, in the constraint that you just don't want to do a lot of damage to your trajectory distribution, suddenly you can derive a whole series of algorithms, and we've been basically living from that for, nearly a decade now. And a lot of people have jumped onto this train. So if you've heard about the algorithm TRPO, for example, that is one of the many special cases of this program, just the linearization of it, or natural gradients for reinforcement learning, which we worked on earlier, are also just linearization of that problem. And it turns out that this KL constraint is pretty much, the more assumptions you then put into the trajectory distribution, but always together with the KL constraint and maybe adding some more constraints, you can actually get really good algorithms which even can be kernelized, which can be put into hierarchies, and which have been driving much of our algorithms. So I'll skip these conclusion things. Now, fine. I hope I've persuaded, I've kind of shown you, given you an intuition of what it means to imitate, kind of match the trajectory distribution, what it means to do, how you should do reinforcement learning when you're living in robotics. You should actually stay close to a trajectory distribution or damage it in the right way so that you get a better policy. And it turns out that that a lot of well-known algorithms which work, but we didn't understand before that they worked, turned out to be special cases of that. of the latter one as well. So now I want to take you down the road where I show you that we can actually learn elementary behaviors quite effectively using these kind of methods. But for that, we need a little bit more insight. Since, well, in the end, we want to learn on real systems. So that means we can at some point have to collect data on real systems. And that usually means that a PhD student has to actually spend a hell of a lot of time. Per forehand, you probably have to spend, for this 1 second or 2 seconds of the forehand, you probably have to spend on the order of 5 or 6 minutes just if you distribute, turning everything on, turning everything off, repairing the robot, and so on. So in other words, big data in robotics is not happening anytime soon, even for the Google guys who try to create farms of robots. Instead, you really need to still understand what prior physics puts onto your and control and motor command generation puts onto your architecture. For us, this is really culminated in that we really want to map from the sense state to the action by, first of all, having one execution layer which always manages to learn all the reoccurring forces, like, for example, gravity, so that you do not need to relearn them for every task. It also has meant that you want to learn specialized primitives and generalize between these primitives for different behaviors, which can then, supported by the execute module, be executed. And finally, you want to have context which allows you to reuse these primitives in specific scenarios. Now let's start just on the primitives and, well, dive right into that. And as a first step, we of course want to do imitation learning. So again, remember, this is reproducing these red asterisks in the one state, one action in your life scenario. Now this is more than one action, since this is whole trajectories. Here you see the robot being taken by the hand, and this is this ball and a string scenario. That's why it's so fast. And, well, you see that the, well, how we collect one data set. And in this case, imitation learning turned out to be enough. You see how the robot reproduces this behavior. So imitation learning by itself was, for us, even surprisingly powerful for that particular scenario. Why am I saying surprisingly powerful? Because I had a really good control engineering master student at that point who spent a hell of a lot of time on trying to create the perfect solution in simulation. The solution from which really looked great in simulation, also his model was, his physical model appeared to be highly accurate. Just the solution which he created never hit the ball more than 3 times and always failed. The learned solution, on the other hand, actually we needed only 1 afternoon of robot time until we had every algorithm, every part of the algorithm debugged, and it worked out. Once we had it correctly, once we had everything correctly running, it worked really out of the box. So it kind of shows you the power, but also shows you how difficult it is to actually make things work on the robot with all the techniques of classical physics. Now, as I've said before, imitation learning is nearly never enough, right? I mean, tennis is a good example. University studies or a PhD are also good examples, since in the end, if you could learn everything from imitation, you wouldn't need all these pesky experiments and trial and error learning. So quite clearly, we need reinforcement learning, so trying to figure out how to reproduce only the good examples and or focus on the good examples. For that, we of course start, just like a good tennis student, we start from the demonstration. And we show, in this case, a demonstration of ball in the cup. Now, I should add here, this robot has a 2-kilogram wrist, and it has no hand-eye coordination at the point when it starts. So, with other words, it has to learn everything from scratch, and obviously it fails already because of the 2-kilogram wrist, which never allows it, it simply doesn't allow it to execute that movement shown by the human. It also can't reproduce any kind of accelerations similar to the human. So the movement is in its peak velocity substantially slower, but the velocity is on average, is much larger on average. Now you see how it improves. And after about 40-something trials, it actually usually gets the ball into the cup for the first time. And after about 90 trials, it becomes perfect. And we've actually had it then that we would let it execute for an open house day for one complete day, and it didn't do a single failure here in that complete open house day. Now, that was of course pretty nice. And I should of course tell you, we also gave it a very informative reward. We gave it the reward of how close did the ball pass by the cup. If you had given it a 0-1 reward, it would probably have taken tens of thousands of trials, and we would have to start at least in simulation. So this informative reward was, of course, of quite some importance. But then again, our human rewards are also learned. So we never take binary rewards. It's right away. We always have a kind of a soft reward function. Yes, sir.
So you've partly answered my question because I was wondering what kind of information was available to the robot to base its feedback on.
Yeah.
So could he feel the ball hitting his arm and
No,
conclusions from this, or does he only have camera feedback?
So we have the position and velocity of the ball, and we have the position and velocity of the joint angles, and joint velocity. And in addition to that, we have the reward signal, which is just minimum distance between ball and cup, achieved along the trajectory. So we had some earlier, and we compared this. So I hope this answers it already. So we compared this also a little bit to a very biased sample of humans. So my PhD student has a pretty big family, and he had an army of cousins whom he all videotaped learning how to do ball in the cup. And he came back and he showed that the 6 to 8-year-old didn't manage to learn it at all. The 10 to 12-year-olds managed to learn it quite nicely in already 30 trials, so much better than in our algorithm back then. And the grown-ups managed to learn it within 3 or 4 trials. So it seems to be only me who took 3 months to learn it. But he also used chocolate as rewards, which is obviously a strong incentive, and instead of numerical rewards. But some of the cousins cheated. We have never seen that for the robot. So now I want to go away from one primitive for one particular scenario, and let's go to reusing primitives for different scenarios. And we started out for that with the dart. And that was one of the problems which I have most underestimated in my life. Since I have thought, well, after doing ball in the cup and ball bouncing, throwing should be easy. And it turns out throwing is a nightmare. So our Barrett WAM, where we trained this dart throwing thing, which I'm only showing here in simulation because we fried the power electronics already during imitation learning. Just due to the high currents going at these peak accelerations. And what we wanted to learn here, which we have learned here in simulation already, is that we have a target always as part of the dart game. So this is an around-the-clock dart game where you always have to throw it to the yellow dot into the same field. And you can obviously learn one dart throwing movement, and then you can start to adapt it to all the different targets. So condition on this additional target. And finally, well, we found in the end 2 robots where we could do this quite safely, so that we wouldn't always have long repairs. One is an industrial robot in southern Germany. The other one, which was in a cage and had a very nice control over the release of the dart, which was our second mistake. We didn't want to have control over the release of the dart, which means if you put a dart on a sled, you need much higher accelerations than if you release it. With the industrial robot, we could actually do it then, and then next to it, we went to visit our friends in Japan who have this Sarkos robot. And there we could actually learn, well, dart games at the quality of roughly a 10-year-old. You notice already, even for that robot, we had to pat the fingers so that it could do the release sufficiently reliable. But I think it's fairly nice dart throws, which you see here, and it's a fairly nice dart game performance which it learns, given for that it's just a robot. Then you can actually give two robots reward together. So these two robots have get a reward if that one catches. They don't know anything about each other. In fact, they don't even know the other one exists. This one only has the ball state in its own state. This one also has just the ball state in its own state. Just we trained the first one with actually a hitting movement. The other one we just gave an arbitrary throwing movement. But they start to align them, and it goes, I think actually within 60 trials, one is figured out to throw it exactly so that the other one can catch it. So now I want to take these. This is for me how we can learn elementary skills. Now I want to take this, and we want to do this with something more complicated. And for that, it actually happened at roughly that time that Bernard Schirkow said to me, "Oh, Jan, I've seen all this now. When are you doing something difficult?" And I asked him, "Well, what do you mean something difficult?" "Well, this was difficult. You have never touched a robot." But he said, "Oh, I was a youth champion in table tennis at some point. Why don't you do table tennis?" And the problem with table tennis, of course, is it's an incredibly hard problem, and we're by no means done by today. In fact, we need better. We figured out what I was already very aware about, what I already knew intuitively from the beginning on, that there are a ton of problems with it. But we nevertheless started this as the first complex skill. And for that, of course, we need now this complete architecture. So we need good low-level control, which I haven't talked about, which could be still a really nice collaboration thing also with your invertible neural networks. You need multiple primitives, and you need context in the context model. And you need to put all of these together. We started with a really naive approach here. So we learned several primitives by mutation, we did self-improvement, and we generalized among hitting points and targets. And here you see how we collect some data. Again, we have better methods now, but this Katharina was really our pioneering person here. We by now have figured out very nicely of how to parse these trajectories then into a library of movement primitives, which requires that we segment them into different phases and then really create distributions over these trajectories so that we can nicely reuse them then in different primitives. And from that, we can obtain different forehands, backhands, waiting postures, and so on, and initialize a supervisory policy. Oops, this was too fast. Now, the supervisory policy in all of our naive approaches actually just combined them naively. So just basically assumed a convex combination of primitives conditioned on the ball would always do a good thing. And this we call the mixture of motor primitives, where this reweighting gives you here, for example, between many different forehands, gives you again a pretty nice forehand. Against the ball gun, you can get as good as 69% of success rate as returns directly from the really few human demonstrations. So that was, this initial really nice success. Of course, 69% is not good enough. So you can now do what a good teacher does, and you could aim the ball gun right at the locations where the robot is bad. And after very few trials, generalization swaps over. You learn how to adapt the primitives in such a way that some of them can take care of that maybe mostly jointly. And altogether, we got it against the ball gun to 97% success rate, despite that this particular region only got to, well, I think, roughly 80% success rate. Now, finally, you see here Katharina at the end of her PhD playing against the robot. And she told me at that point she learned table tennis for her PhD. And as her PhD advisor, I'm probably not allowed to say this, but I think the robot is about as good as she is. Now, I should say, we have by now methods which do faster imitation learning, and there's a lot which has happened since then. So stay tuned for the, well, next couple of upcoming papers.
I'm sorry,
Yes.
where is the camera?
Okay, so cameras. When you look up here, you can actually recognize one of them. So in every corner of this room, there's a camera. These all look at the ball, and I will tell you about 3 more cameras a little later. One little later part of the talk. Yes, sir.
And the feedback signal for the robot is how close it misses.
In this case, we gave the robot just the reward for hitting onto the table, which gets smaller to the sides. So, now I told you already from the beginning on that this was a very naive approach. And the first thing which one of the next things which we did was that we decided we wanted to learn a task which is, well, more nonlinear, where there's not so long flight times of the ball, where there's more nonlinear, more unpredictable behavior of the ball happening. And we decided to do tetherball. And for tetherball, you have a big pole in the middle, and you have a ball on a string, and you're trying to wrap it up. And in this case, the naive approach falls apart. Convex combination of primitives is no longer possible because it's not like that, because there can be 2 very, very different movements which are not combinable in their outcome, which can happen there. Kind of the classical scenario of the pilot has to go around the mountain to the left or to the right, but if you average over these solutions, you go right into the mountain. Now, in this case, you really need selection, and the first way we did this, well, first we saw that the naive approach completely failed. So here you see the different trials from 2 different motor primitives, and you notice this is here would be a good solution, and here would be a good solution, but combining them would probably be suboptimal. But what actually happens is that our learning system will not really differentiate these 2 primitives. So then we recognized that there is a very simple idea of how we can extend it by just forcing our context system to have only a limited amount of entropy, so a limited amount of responsibility, so that not every primitive can try to grasp every behavior in this hierarchical solution. And then actually the solutions nicely spread out, and it gave us even a tool to now figure out how many primitives we need. In Tetherball, this has actually allowed us to, well, find with this hierarchical reps approach, it has allowed us to figure out, get a good reward really fast, and better than the 2 competing approaches. And in addition to that, we could actually figure out how to get rid of quite a lot of the primitives, starting with about 30 primitives from imitation learning. We would get, in the end, to I think about 13 or 14 primitives within relatively few trials. The naive approach can also get rid of primitives if they're no longer activated, but this was, well, it has substantially lower reduction. We also employed then this approach in sequencing for manipulation. Here you see different tasks. So this here is a stacking scenario done by Oliver Krömer, who's now a professor at CMU. This is a pepper mill task, also learned by sequencing of primitives, also done by Oliver Krömer. And then this here was a bimanual task done by Rudy Lutikov. who's now a professor at UT Austin since this year, so he just graduated last year, who learned how to saw an eggplant. And please recognize the difficulty is actually the hands holding the knife, not it's not a software limitation. This is actually a hardware limitation. This was the best you could get out of these hands. So, now I hope to have given you the picture of how we can create a learning architecture, how we can do imitation learning first. If we want to do all the learning on the robot, we don't want to move to a learned model and we don't want to move to a simulation, then we should always start with an imitation and subsequently self-improve. Now, the last question which I still want to address is I want to take this architecture which we came up with through the first three questions and use it in order to adapt to humans. And this really goes back again to robot table tennis. Since back then we asked ourselves, well, what actually are the key limitations for table tennis? And one thing is clear to anybody who has seen our setup. If I take any of you, nail you to the ceiling, and then make you play table tennis with a racket on a long stick, well, you're going to be terrible, right? Humans are so good because they sidestep, and by sidestepping, they can reuse their strikes many times and can perfect them. And so quite clearly, this workspace limitation is a core one. The second core limitation is that our arm accelerations are terrible with a Barrett WEM. Again, if I would take this is only 1 kilogram. Now imagine I put 2 of such bottles and I again nail them to your wrist and then you have to play table tennis. I hope that was okay. I'm pretty sure that you're gonna have a pretty hard time playing table tennis because you have to do fast but slow acceleration movements, and you have to figure out how to brake again so that your arm, well, doesn't break. This is quite clearly a pretty hard problem. And then there was a third problem. And the third problem we actually did not realize initially we had. So we, at that point, started to study human strategies. We got all of these European champion level table tennis players. We put them in a tracking hall. We started to try to understand their strategies from in a Vicon tracking hall. So we no fancy computer vision, unfortunately. And we started to study how do they actually do it. We started to use inverse reinforcement learning to recover their reward functions, which turned out to be pretty boring since it turned out that naive players and professional players have pretty similar reward functions, only that the professional ones have much better abilities, which allows them to employ them much better. And then they said to us, then they looked at our setup and they told us something which totally puzzled us computer scientists. They told us, why do you have cameras looking at the ball? We said, of course you need to look at the ball. They said, no, we are trained to never look at the ball. We are trained to only look at the opponent. And now that was for us quite an insight, because there was a point when we started to study the human sensory motor system, and that's turned out to be a problem we shared with the human problems. Now, the first two problems you can only solve by creating a muscle-based robot and put it on linear axes. And I guess the two most renowned experts on muscle-based robots for robot table tennis sit in this room as well, and some of you have seen Simon's talk today. So at some point I do hope to see this. And since that's really the only way of how you can address the first two problems. But the third problem, the limited reaction time one, turns out to be actually much more relevant. So I want you to watch this movie. Wait, I want to watch this movie one more time, very carefully. Now here is the last moment where this baseball batter can use any visual input. Now you must imagine, this here is like 15 meters. The baseball batter is hitting with a bat the ball which is about as big as my fist, and the bat is like my arm, from 15 meters away. There is no, and he doesn't get any visual input there. There's no way you could get this is just by, well, accurately predicting the ball trajectory alone. You need maybe a part of it, but that's not going to be it. So, but instead, what he really needs is he really uses, and this in baseball really well studied, he uses the trajectory, the arm trajectory of the guy who throws, the pitcher, and predicts from that what kind of curveball that is, and so that what kind of spin is in there in order to get it right. And well, that triggered for us a lot, and it turned out to be highly relevant in table tennis for the simple reason that in table tennis we have, well, when humans play exactly the same problem, that a very small change in the spin axis does make all the difference. And so one of my PhD students, and that's Jikun Wang, he actually started looking into this problem. And this here is the ball about 300 milliseconds before Jikun, who's at that moment here, hits it. This here is, I think, about 120 milliseconds. This is like 80 milliseconds. I can be slightly wrong on the numbers before he hits it. And what you, of course, want to have is what you will have is a more and more accurate distribution of where the ball will go, where Jikun will hit it to the robot. So we are trying to predict Jikun's movements, in this case, before he is even done them. And it turns out that 320 milliseconds before Jikun has touched the ball, you can predict with an accuracy of 35 centimeters where he will play it. He did, of course, not just use himself as a data set. He actually averaged over multiple PhD students and some people who actually play in table tennis clubs and are not computer science and are computer science challenged and not sports challenged. So it actually works quite well. When you get down to 80 milliseconds and you use the best method he came up with, this you get nearly 30 centimeters. And this shows you, well, kind of how well this works. So in this case, we are just having 3 primitives, and he wanted to make it overly demonstrable, so he always had the robot go to a preparation posture and wait in advance, so that it would show what kind of movement it would do just based on the opponent's movement, and well, you see how it. You basically see how well the robot actually does, that it does forehands and backhands and the middle movement quite frequently in exchange to each other. And yeah, good. I don't know, time-wise, I guess I'm running low now. Yeah. So I'll skip the last. I'll skip the last part. We also have been using this for interactive tasks, for interactive assembly, and tasks which are closer to industry, so that we get funding which doesn't come from Max Planck, which also funds fun stuff, purely fun stuff, and it's been pretty successful for that as well. So let me, for that reason, finish now with. Of course, it's not all table tennis what we do. What we're really addressing here is a core problem. In first world countries, we cannot produce without robots. If somebody tells you how afraid they are for robots taking away their job, remind them we would not have a car industry in Germany. That means about 40 to 50% of all jobs are directly or indirectly connected to the German car industry. We would probably lose 40 to 50% of all jobs in Germany without it. If we weren't so good in industrial robots in Germany, we would not have a car industry. But on the other hand, there's a ton of other industries which cannot produce in Germany simply because, or not even Europe, or not anywhere where outside slave labor conditions, where you have people really do awkward things in awkward situations, for the simple reason that robot programming is too expensive. In order to, if the world productivity, in order to make it rise, you really need to bring robots everywhere. And like in Germany, you could never do this if a product costs less than 50 euros and is produced less than 10,000 times, simply due to the cost of robot programming. Now that is something we hopefully can change with the methods we are developing. What you can already show is that in rehabilitation, they're quite practical, where basically supportive technologies can use the same kind of scenario of just a human rating now as a reward. Human says, well, this felt better, this felt less, not so good. You can actually create relatively nice rehabilitation devices, which even had, well, some empirical impact on real patients. And finally, well, I still want to have a robot at home so that this nasty kitchen finally cleans itself instead of, well, me cleaning it up. Altogether, core topic is machine learning for robotics of both this talk and my lab. But we highly relate to classical robot engineering. We do a lot at the core robotics scenario and really try to understand things from that perspective. While we also develop machine learning methods purely for which are could be applied to arbitrary problems, not just to robotics. And we are really interested in how do humans and biological systems do what they do, since for us this is still the most amazing teacher you could have. And well, for robot engineering, we have been doing tactile perception. We do a lot of simulations. We work with many companies. We do nonlinear control. We have to do some high-speed vision. There, we would love more of your support, Carsten. Vision people who touch robotics problems are very rare because they're, well, never mind. We do a lot more grasp manipulation. We do a bit of humanoid robotics. And we even do stability proofs for control laws, and we try to automate them in order to, well, assist the robotics and control engineers. In terms of machine learning, well, we do way more method-related things. That's also one of the reasons why we're at Max-Planck in addition. And in terms of cognitive science, we work with the Moritz Grosser-Wentrup and the Tübingen University also with the brain-computer interfaces and brain-robot interfaces. We really want to understand how humans play table tennis and how they do movements, and maybe even what kind of infrastructure there is in human brains for that. With that, I'm at the conclusion. I hope I've persuaded you that motor skill learning can maybe at some point help us avoid programming all the possible scenarios, that we have some really nice imitation and reinforcement learning methods which can actually learn things on real anthropomorphic robots. And, well, that things as tough as table tennis are, to some extent, doable with that. With that, I would like to thank you for your attention, and, well, I hope you have lots of questions.
Hello, good evening. My name is Jan, too, so that's a great coincidence. Thank you so much for the presentation. It was really entertaining. In fact, I was really surprised that just with a handful of tries, you can teach rather complicated policies to robots. And you said that big data hasn't arrived in robotics yet. When I think about robotics, or in particular reinforcement learning these days, I think about deep reinforcement learning. I think about OpenAI, and I think about all the impressive things they have done by using the same model and generalizing it to a whole bunch of different use cases. However, these models, they rely on a lot of input data or training data, and they are usually trained in simulators. So do you think that the future in robotics lies in having algorithms that rely on less training data, or having simulators that are more accurate to the real world?
How much should we learn in simulation? Now, you can break a robot quite quickly when you train in simulation. In fact, the first thing I did with the Barrett WEM, which you saw, was that I wanted to be real fast, so I decided I'd learn a simulator there, which, well, a forward model, a simulator, and I trained my policy in it. And I really quickly impressed everybody by showing some really fancy movements. And what happened? Well, the first thing which happened with the policy, which looked great in simulation, was it made bang! It went to the joint limits. I think it made a little wiggle, and then it made bang and went to the joint limits. So, and the terrible thing is the Barrett Ram is an American-built robot, so it doesn't have any clutch or anything which limits, which saves the robot from the joint limits. So so that also meant it was directly broken. So basically, first thing as group leader, I had to also go to the director and say, hey, you just bought me this beautiful robot. Now can I have 10,000 euros for repair? Beautiful. But the important lesson in there was the parasitory effect, which was modeled in there, badly modeled by the system, was actually just due to regularization. It wasn't actually more than regularization, that in a tiny region, you would have the sign of the sign of the slope of the function slightly wrong. Very tiny difference. Really, you would not see it since everything was in this less than 1/10 of a Newton of an error in the model. So the model should not have. You would not be able to see this from that. This would have been a bad learned simulator from the real system. So it was so incredibly accurate. But this tiny error in the slope, of course, told the optimizer to say, oh, if I'm just wiggling really, really fastly, and then do one big step in this, I basically get energy for free. Since wrong slope on something which is friction-like, well, obviously tells you, ouch. So very accurate simulator, very accurate learned simulator, even from data, was not enough to prevent this. This we've by now studied, and we understand it to some extent, and this is the so-called, what we call the simulation optimization bias, since your optimizer is guaranteed to exploit all the errors of your simulator. So the best case, it gets 0, but it's always overestimates its abilities on it. Now we try to address this, of course, and we figured out an algorithmic approach of how to address this problem. It is basically that you have to average over a large number of scenarios, and by that estimate how much of this bias could still be around. And so you basically destroy your world in many different ways, and you compare, and only if you're good over many worlds, then many different mechanic worlds, you actually accept the solution learned on the simulator. Still, simulation is doing things in simulation which actually then work on the robot without further trials is super hard, unless you have tweaked your simulation to be perfect. And that usually it requires even a physical understanding of everything in there to an extremely high degree. So yeah, I can discuss. This could be an evening discussion.
So my question also aims at the data availability
Mm-hmm.
problem. Did you ever try, nowadays we have wearables, and especially like for tennis training, you can actually record your arm movements and then basically adjust on this your swing and so forth.
Mm-hmm.
Did you ever try to combine this so that the human actually wears some kind of wearable and also the robot, and then you match basically the imitation also during the training phase? And continue this.
Interesting. So no, we've never tried this. We tried at some point. We took a long time ago the Nintendo Wii and wanted to use it as a teaching device, because it's actually not that easy to take the robot by the arm and teach it table tennis movements. But it's somehow this was never good enough that we were happy with the demonstration quality. That we could have probably extended into this direction. But it's a cool idea. Sadly, we may not have the bandwidth at the moment. So, but it would be nice to do.
If you consider this challenge, bringing everything of this to industrial application, you've showed a lot of progress on the computer science part, and you, in the introduction, basically said a robot in industry today looks as it did in the 60s.
It looks not. The industrial robots today look much nicer than the one from the 60s. But the technology which they have in between is basically the same.
Yeah. So what do you think is possible with current technology from industrial robots, and what is missing to apply all these nice things to current industrial robots? So how far are we from applying this to industrial problems?
So at the moment, we actually moved incredibly close to that, and in the last decade, I should say, in terms of the cheaply available technology. So pretty much 10 years ago, the DLR lightweight arms became available at the company KUKA, which at that time at a price tag of about exactly 100K euros, with which you could actually do, at least from the arm point of view, everything you would need. Now, that's of course, so that back then would be a rather high price tag, because a typical off-the-shelf industrial arm costs about 15K euros, and it is not the real, it's actually the cheaper part of it's cheaper than the programming of the robot. But, so at that time this wouldn't have paid off. But by now, well, KUKA then got sold, apparently for very little money, and this brought the brothers Haddadin, Simon and Sami Haddadin, to the idea that they founded a company based again on taking the DLR designs and one more time redesigning this robot such a lightweight robot from scratch. And they did this so smartly and so well that they ended up cutting the price by a factor of 10, so that they can sell them now for 10K euros. And by that, price basically says a teachable robot plus the right software should be substantially cheaper than buying a classical industrial arm and using classical industrial programming. And at least for most areas of application. So I think we're very close to this scenario now happening all over.
So maybe we didn't get it, but have you ever tried to learn the physics of the system so you get
Sure.
the simulation right?
So first of all, we've tried all the different combinations here. We've even tried, we've been parameter estimation and physical models is interesting for us, as we've worked with that from the very classical robotics perspective. It's surprisingly difficult because despite that mechanical systems, when you learn the inverse dynamics model, are linear in the parameters, they nevertheless, the constraints on these parameters are unfortunately, non-convex, and not every solution is good, which you can get out of that. And it's surprisingly easy again to get something which is unstable and breaks your robot, just using the physics equation, just wiggling the robot around. At Franka, for example, they really take the robot apart and measure every single part before they screw it together in order to get the physics model more accurately. That just gives you the rigid body dynamics. It doesn't give you any actuator dynamics or anything else. And what we have done, what from our experience works best when you want to get a physics model, is that you first take all the derivable physics equations, like let's say a rigid body model, a primitive approximation of your actuator dynamics, and you put this into the mean function of a GP. Treat all the physics parameter, initialize the physics parameter by the best data you have, but then treat them as hyperparameters of the GP. And then with the GP, approximate the rest of the dynamics. It works reasonably well whenever you can, for like an inverse dynamics model, whenever you can have an additional small PD controller around it, which makes sure that you don't become unstable when the combination between, the approximation error of the inverse model and the true forward system don't give you an identity. But you still need a controller to make sure that you get the stability there. I think actually, maybe I could even show some more video on that. Oh, never mind.
Two short questions, and then there's Jan available. You stay
Yes.
with here. We
Yes,
have
absolutely.
Pizza as well coming up, right?
Sounds good.
Right. Yeah. Great.
Yes.
So, okay. So, one question.
So you mentioned the problems that you have with the simulation. So does that not also transfer to the actual hardware? So let's say how transferable is such a solution to another hardware? So let's say you have same robot twice, but given that all these small changes or physical variances are kind of avoided by the learning, it's not really transferable from one system to another, right?
You probably can learn a bit faster if you're starting from one to the other. But I'll give you a very famous example of how terrible it is to move robot programming from one robot to another. So about 3 years back, there was the DARPA Robotics Challenge, where I think 15 labs all got the same Boston Dynamics humanoid robot. In fact, my colleague Oscar von Strick in Darmstadt also got one of these, albeit they had to work in the US for it. And this is the video where when you now look into this famous video of all the robots falling down, that's actually the same challenge. And it turns out that the same program, they had to always do this in the American military style, so they had to program it on their own robot, and then they had to transfer it to the military robot, and every single one of the programs failed on their robot. And they interchanged the robots, and it really turns out the transferability is of simple hard-coded programming, which works perfectly on one robot, doesn't tell you anything about the other robot, built in exactly the same way by, well, still one of the leading companies in humanoid robotics. Now, I think for arms, we can get there. I don't think this is going to be a problem. For whole humanoids, it's the intervariability. This is going to take a long time. We need much, much better algorithms there on the long run.
This might even degrade over time, right? As it's just
yes,
hardware, so
absolutely. Wear and tear, heat, a lot of things make a difference there and can do a difference. In fact, I think this is again one of the reasons why I'm so much pushing for learning solutions, since they remain adaptive, why we should model things more by distributions so that we can grasp that we are robust over a larger number of scenarios, so that you are not caught in exactly this one physical scenario which we have modeled. I mean, I'm not saying that physics can't be fantastic here. I'm just saying that, well, physicists actually know this, that distributions are good. Engineers don't know this, so.
And one more final question. One quick question, like what's after table tennis?
Oh, I want to push table tennis for a while longer still, since at least as long as Max Planck wants me to do this. I think generically, I would love to, at some point I really want to do more in terms of actually, well, bring these rehabilitation and industrial scenarios forward. Right, since I think this is going to be relatively interesting. And in the end, I think the two hardest parts of robotics are always either high speed, like in table tennis, or a lot of contact with the environment, and as a manipulation. And everything, well, all the problems which don't fulfill these two are the easy ones. These are the really two hard domains. Well, if you ever solve table tennis, I'll definitely want to solve the other one too.
Okay.